Hi everyone, today we will be on the third lecture of the module 5 and it would be the lecture about the capacitor. So today we are going to follow the handout 4 about the capacitance and the dielectric. So here I'm going to first summarize the theory behind the capacitors for you, and then we are going to work through the examples. So uh, So the learning outcomes for this lecture would be about for you to be able to find the value of the capacitance by using the definition, um, and you'll be able to find the value of capacitance from the system of plates, and you'll be able to find the capacitance from the system of sphere and cylinder. And then from finding the values of capacitance for one capacitor, will be moved to consider the capacitance in the circuits where the capacitance can be connected in parallel, or it can be connected in series, or it can be connected in the mixed circuits. And we'll be able to calculate the energy that is stored within the capacitors. And then we considering the dielectric materials that can increase the values of the capacitors. And finally, for the next video, next lecture, we'll be talking about the RC circuits, which is also in the lab 3 of the PHY 192 module. Okay, so we start with the definition of the capacitance. So the capacitance is defined by the ability to store charge. So you can see that from this equation, V would be the voltage difference, or we can say the potential difference between, let's say, two metal plates. Okay, so if I start with this metal plate, given DC source to the metal plate, so the current will be flowing from this direction on the positive into one side of the capacitor, and electron will be flowing from the other side, causing the negative charge on the plate. And it would cause the potential difference between the plates, because positive charge will cause the positive potential and negative charge will cause the negative potential. Okay, and we want to know about the ratio of the charge Q on the plate if we are given the voltage difference of 1 volt. So here we are saying that the capacitance would be the ability of the system to store charge when given a potential difference of 1 volt. So if you give higher voltage from the source, your capacitor will be collecting like more charge. But if you have the capacitor that is pretty good, or having a high capacitance, using only small charge, using only small potential difference, you can collect like more charge. Then for the energy in the capacitor, we can be using the U for the energy in the capacitor, in which Q is the amount charge, C is the capacitance, and V is the voltage difference. So how to derive or how to prove these three formulas will be coming from us using integration of voltage and charge. So we integrate VdQ and from 0 to Q. So this is about charging the capacitance from from the having absolutely no charge until we have the charge of Q. So I'm integrating this equation, and it would give us the integrate of Q over C dq, because from the definition, if I have C equals Q over V, V would be equals to Q over C, and C is the constant we bring out from the integration, and then I integrate the rest of them, and it would give us Q square over 2. Okay, so that we have the Q square over 2C, and then using the same definition, C equals Q over V, we should be able to show that U would be also equals to half CV square and half QV. Okay, so let's summarize what you see from this board again. That the capacitance is the ability to store charge. When you give the potential difference of 1 volt, we ask for how many charge stored on the plate, and that is the capacitance. And not only storing charge, but the capacitance also like holding up the potential energy, and the potential energy can be calculated from these formulas. Okay, so the next concept we're talking about is how to find the values of the capacitor. So here I will provide you 3 steps of calculation. We will start with having electric field. Then from electric field, we should be able to find the voltage. And from the voltage, we should be able to find the C. So how to find the electric field? So not only the Coulomb's law, but there's also Gauss's law that you can be used as tool for finding E, or the electric field. And from the electric field, you should be able to find the potential difference by integrating the electric field with distance. And when you got the voltage different already, so you can use the definition of the capacitor, the capacitance, to find the capacitance C. So, for example, if you are given a system of rectangular plates of a parallel plate, and you have the parallel plate of area A and of the separations D between 2 plates, then the C, or the capacitance, can be calculated from epsilon 0 A over D, when this epsilon 0 is called the permittivity. So this is the same epsilon 0 that you have from the electrostatics. Okay. So this permittivity is equals to 8.854 times 10 to minus 12. Okay, so this unit, we can say that this unit is farad per meter. Okay, so how to prove this? Okay, so firstly, we try to apply the Gauss's law for the parallel plate. So from Gauss's law, if you are given the parallel plate, you can see that from Gauss's law, your electric field would be found coming out from the positive pole and going into negative. So as we have the total charge within this closed surface as 0, you find that there will be no electric field outside. So electric field would be only inside the plates. Okay. So for Gauss's law, we can we can write down the electric flux as just EA. Okay, and from the EA, we have the Q on one plate and over the epsilon zero. So that now electric field would look something like Q over epsilon zero A. And then from Gauss's law, we should be able to find the potential difference from this equation. So it is integrate E dot dr. But as E is a constant, okay, so this equation can be reduced into the form of V equals ED, right? And from V equals ED, what we have is we can substitute the E from this side onto this side, and I come up with QD over epsilon zero A. And finally, to find C, I use C from the original definition of capacitance as a charge per volume. So from this charge per volume, then I should be able to prove that C is actually epsilon zero A over D. So that we can prove that the capacitance of the parallel plate will depend on the area. So if you have the larger area of the plate, it tends to have the higher capacitance, or this system will be able to carry more charge. But if you have the gap between two plates, the large gap between two plates, it means that you have the smaller C, and you can carry the smaller charge. Okay, so after that, to find the capacitor for the capacitance for the cylinder. Okay, so here I have the system that contain the two cylinders. So one is outside and another is inside. Okay, and then we connect one of the plate with the positive pole from the DC source, and then we connect the other with the negative. Okay? Or you can either write down the DC source like this. Okay, it's the same thing, right? So we say that we put positive charge onto one side, put the current onto one side, and the negative charge will be put into the other side. Okay, so from we having positive charge within the inner plate of the cylinder, and we have the negative charge at the outer plate of this cylindrical capacitor. Then we can show that the electric field would be in the direction that coming out from the center. Okay, so this is coming out from the center. So, and we can then show that C, or the capacitance, will depend on L, or the length of the cylinder, and would be depending on B and A, which are the outer and inner radii of the cylinder. Okay, so again, we follow 3 steps again. Gauss's law to find E, and from E we find V, and from V we find C. Okay, so I will start with Gauss's law again. So using Gauss's law to find this electric field. Okay, so I'm going to use the magnitude of electric field to times by the area of the cylinder. So if I consider the Gaussian surface, okay, let's say the Gaussian surface, that is made from any cylinder of radius r. Okay, so then I would have 2 pi r L as the area of the cylinder, and that it would be equals to Q over epsilon. So electric field can be found from Q over 2 pi epsilon L and times by 1 over R. Okay, so you can see that now electric field is not a constant, so it's different from the case of parallel plate. For the case of parallel plate, we found that E, or electric field, is a constant, but not for this case. For this case, you can see that E is depending on R, right? So when E is depending on R, okay, in the step 2 to find V, we then need to integrate, right? So that's if I follow this definition of minus integrate E dot dr, okay, and when E is in radial direction, integrate E dot dr would be just the product between E and dr. So I'm going to integrate, okay, put this constant out of the integration, and I'm integrating 1 over r dr, and integrate from A to B, right? When A is the inner radius and B is the outer radius, so we can see that electric field is coming from radius A to B, is between radius A and B. So I integrate from A to B, right? And then we can find that when integrating him, so V, or potential difference, will become minus Q over 2 pi epsilon 0 L, and this will be the ln of B over A, right? So so number 3, to find C, I consider the ratio between charge and the voltage difference, in which here for the voltage difference, I'm going to use the absolute values of the voltage difference calculated from step 2. So that C would be Q and over Q over 2 pi epsilon 0 L. These guys are all the constant, and ln B over A. So then Q can be cancelled, and finally we got C, or the capacitance, that depends on the length L and depends on the size of the cylinder B and A, so inner and outer sides. Okay, so here I have shown you how to calculate the capacitance from the system of parallel plate and parallel cylinders. Okay, so I will let you do the one with sphere as a homework, but it's not so difficult. You can be following the steps on finding the capacitance of spherical capacitors on the third page of your handout. Okay, so they contain the integration steps that you can follow them pretty easily. Okay, so so now we have been working on finding the C for plates and for cylinder. Okay, and the next topic would be about trying to connect the capacitors. So you might have some background on connecting the resistors, right, from last week. So for resistors, okay, you have that in the series configuration. If I have R1 and R2 connected in series, we know that R total would be simply R1 plus R2. Okay, and if we have the parallel configurations R1 and R2, so we have that 1 over R total equals to 1 over R1 and 1 plus 1 over R2, right? So how to prove these relationships? Okay, you can find out the details from last lectures. Then we are considering how to connect, how we can find the total C or the total capacitance when we connect the capacitors in series and in parallel. Okay, so then let me just prove something for you first. Okay, so if I start with considering the series, we can see from this picture that if I give some of the current with positive charge on it, and positive charge would be crowded on the upper side of this plate, right? And at the same time, and okay, so maybe let me start with this first. Maybe if I have like two capacitors connected in series, right, like this, and I give it a voltage by applying the DC voltage. So we will have that. Firstly, when the current flow from the positive electrode of your battery, and electron flowing from the negative electrode of your battery. Okay, so first thing that happens is the negative charge will be crowded on one side of the capacitors, and the positive charge will be crowded on the other side. But what about the things that happens in between? So if you remember about the electrostatic induction, okay, so if you have the positive charge, and if you have that the charge positive, negative, positive, negative, which could be electrons or hole in the materials, okay, so by the principle of charge induction, okay, positive charge that you have in the system will be automatically drawn to the lower capacitor, and negative charge will be drawn to the upper capacitor. Okay, it's just because of the Coulomb. It's just because of the Coulomb interactions between positive charge and this negative charge, and the Coulomb interactions between this negative charge and this positive charge, and the nature of this part of your circuit. That is a conductor. And then don't forget that for the conductor, charge can be moved freely within the conductor. So when the charge can move freely, they just choose where they prefer. So negative charge prefer to be with positive charge, and positive charge prefer to be with negative charge. And then we can roughly say that the amount of charge over here, if this charge on this plate is plus Q, the charge on this plate must be minus Q to cancel out. And the charge, if the charge on this side is plus Q, the charge on this side is minus Q. So that is why the Q, or the total charge in the series circuit, would be equals to charge at capacitor 1 and the charge capacitor 2. Okay, so that is the reason. So the reasons just come from the electric induction between that, and come from the nature of the conductor, that electrons and holes can move almost freely there. Right? So we have that Q equals Q1 and equals Q2. And as a result, okay, if I then reconsider this definition, so so from Q, from C equals Q over V, Q would be equal to CV. So that I have C this way. I have C total. And C total and V total. Okay, so equals to C1 V1 and equals to C2 V2. Okay, but we have that V total is equals to V1 plus V2 because they are connected in series. So this is making sense that if this is V1, this is V2, the V, or the total V, would be automatically the summation of 1 and 2. And then if I use the definition again, so Q equals C over V, so V would be equals to C, sorry, I think, yeah, the definition is C equals Q over V. Yeah, sorry about that. So V would be equals to Q over C, right? So that Q over C here would be equals to Q1 over C1 plus Q2 over C2. Okay, but we have that Q is equals to Q1 and E is equals to Q2, so we cancel out all the Q's here, and therefore we have that 1 over C is equals to 1 over C1 and 1 over C2 in connecting C's in the series. Okay, so you can see that connecting C in the series is giving the opposite formula from the resistors. Okay, so that was the proof. But if you are remembering this formula for exams or for practice, just note that R in series, you just plus it. Okay, but C in series, you need to plus the inverse of the C, right? And then for the parallel configurations, you have that V, or the voltage, is equals to V1 Okay, and also should be equals to V2, right? So these are the things that they have in common. And we should also have that Q total, the total charge, is Q1 plus Q2 this time. Okay, so when we have like the Q total like that, I substitute CV equals C1V1 plus C2V2. But as we have that V is equals to V1 and is equals to V2, we can cancel all the V's here. And we have that for series configuration, C would be equal to C1 plus C2, right? So that would be way opposite to the resistors. So and this is making sense because if you think about this plate as this plate as the system with the area A, okay, you when you try to put this guy in parallel, it would just be about you trying to increase the area of the system. Okay, so as C depends on A and D, adding up the capacitors in parallel will be just the way that we could increase the A or the area of the system. So we can then for this we can calculate the C total from simply adding up the C, right? So let me summarize for you again. Okay, so what we have so far was the definition. Okay, the definition of the capacitance Q over V, and how we find the energy for the capacitor, and then the steps of finding the capacitors by E, V, and C. E, we use the Gauss law. We use the product between E and R, and C is Q over V. We will be able to prove the C values for both parallel plates and cylinders. Okay, and then when we try to connect capacitors and resistors in series and in parallel, the way that you can remember this easily is it's just going to be way opposite from what you did in the resistors. So if resistors connected in series, you simply add up the R. Okay, but if your capacitor is connected in series, you need to add the inverse of C. But with the parallel configuration, the total resistance for parallel R1 R2 can be found from adding up the inverse of R1 R2. But for C in parallel, we just add up the capacitance in the system. Okay, then the last topic for today would be about dielectric. So dielectric would be the material that we put into this material into a plate capacitor. Okay, so so just note that what happened. Okay, it would be the ability of dielectric to adjust the opposite charge. Okay, so what you see here, okay, here I would try to compare like two capacitors, one with no dielectric and one with dielectric. Okay, and then we see what happened now. Okay, so one with no dielectric, if I give amount of charge let's say 4. Okay, and this is what we have for this capacitor with full capacity of charge. But if we add up a dielectric material like this, okay, the ability of dielectric material is, so if I got the positive charge here and negative charge here, in the dielectric, there will be the charge, some charge or some dipole moment that they kind of like response to the electric field of the system, and we are going to have the opposite kind of charge at the interface. Okay, but in order to maintain the voltage, okay, in order to maintain the voltage, so that you here you have seen that here the voltage must be formed the 4 positive charge and 4 negative charge. But if you have this negative charge at the surface, so now you can see that your total charge would just become +1 and -1. Okay. Meanwhile, it start with like +4 and -4 here, right? So the thing is, the voltage source would try to balance the voltage, that input, and the charge, so that more charges like this, and this, or this, and this, okay, would be added, so that's the total charge for each plate would not be 1 anymore, but would be 4 and would be -4. But you can see that on this region, we have the charge at the plate of 7, but not only 4 anymore. So this is the effect of the dielectric. Okay, but in terms of properties of the material, we have the K or kappa, or the dielectric constant, which is a constant for many kinds of material. Okay, and with that, to find the capacitance of the capacitor with dielectric, you can just simply timing the dielectric constant to the capacitor of to the capacitance of the capacitor with no dielectric. Okay, so just give you an easy example. Okay, so for example, if I happen to bring the rubber to be my dielectric material here. Okay, so firstly, if I have the C of this parallel plate capacitor as epsilon 0 A over D, like this, we just call this guy the C0, or the capacitance, in the case that is no dielectric material. But if I add up the dielectric material, so the dielectric constant of rubber is about 6.7. So with the same parameter, with the same A and with the same D, okay, the capacitance of the capacitor with dielectric would be like 6.7 times the C with no dielectric, right? So so that is the thing that if we use the different materials, okay, we use different material, it would result in the different values of the dielectric, and it would also result in the difference in the values of the capacitance itself, right? So that would be all the equations and theory I've read. Okay, so maybe if we summarize like everything once again. So firstly, we have the definition for the capacitance. Okay, as C equals Q over V. Okay, in which we have the plate with the charge plus Q and another plate with the charge minus Q, and connected to a voltage source. So C from this, okay, C from this would be defined from Q over V, right? But if we think about like the dimension parameters like area and the gap distance D, okay, then we can find that C is equals to epsilon 0 A over D. Okay, so this one is with no dielectric. But if your capacitor is with dielectric, you can find that C would be equals to kappa C0 and would be equals to kappa epsilon 0 A over D. So you just simply timing with the kappa when you change the kind of the material. Okay, so now let's jump into some of the examples. Okay, so for number one, they're asked to calculate the capacitance of the spherical conductor. Spherical conductor of radius r. Okay, so now let's start with considering a sphere conductor. Right. So if the conductor is a sphere, okay, we can have that if there is some excess charge, all the excess charges would be held at the surface, just under the surface of the conductor, right? And then from here, we should be able to find like the electric potential of this sphere. Okay, so if I start from Gauss's law, okay, so we can find that E, or the electric field at the surface, okay, would be equals to Q over 4 pi epsilon 0 r square. Okay. and would be Q over 4 pi epsilon small r square, okay, at distance r. Okay. Then if I want to find the potential, okay, we follow this integration, and then I would integrate from the surface R to the infinity, in order to find the potential for this sphere. Okay, so integrate the constant Q over 4 pi epsilon 0, and we have 1 over r square dr. Okay, so from the integration, I put out this constant and I integrate 1 over r squared then. Okay, so what should come up would be 1 over r, just 1 over r. Okay, and let's take like the lower upper limit, okay, from r to infinity. Okay, and then you find that V would be equals to minus Q over 4 pi epsilon 0 r, or the absolute of V is Q over 4 pi epsilon 0 r. And finally, we use the definition of the C as the charge that's stored within the capacitor, given just 1 volt, right? So C equals Q over V. So by doing that, we have that C of the C of the sphere of a sphere will depends on the radius r of that sphere. Okay, so next example. So we discussed about a defibrillator, or a device for treatment of cardiac arrest. So that they give us the information of C, the capacitor, and then they say that the capacitor here is having the energy of 300 joule, and then they try to ask for the voltage that would be used. So we can come up with the energy formula. So from the energy formula, you can choose to remember just maybe just one formula from here, and then just one formula from here. So half CV square half QV, or Q square over 2C, right? But the one that we actually need this time would be this equation. And then I think that we should be able to find out about the voltage, just only rearranging the equations. So that would be like 2 times by U of 300 joule, and divided by C of 300 microfarad, or 300 times 10 to minus 6, square rooted. Okay, and then what I have over here would be something like 1,400 volt. So this is the voltage that we actually use for rescuing the patient with the cardiac arrest. Okay, so here are this part are the theory about finding the C for the spherical capacitor. Again, you can see that they start from having E. So this is what I mentioned as the first step for the calculation, and then they come to find V from an integration, and you use definition of C equals Q over V to finally find out the C. The same goes for the cylindrical capacitor, in which I already showed you. And then for connecting the capacitors, we have the part that showing the proof that I have done before. That for connecting in series, we need to add up the inverse of the C. But connecting in parallel, we just need to add up the capacitance itself. Okay, so now there's an example for us to calculate the total capacitance of the circuit. So from this, I would just easily consider the total capacitance of 2 and 3. So with 2 and 3 being parallel, I can just do C2 plus C3. And then for C total, okay, here you can see that C total having C1 and C23 in series, right? So when it is in series, we have this 1 over C total should be 1 over C1 plus 1 over C23 that we found out before. So here's C23. If you find out the values, so you should be able to find that it is C23 is 25. Okay, and then for C total, so let's rewrite this equation for C total. It can be rewritten in terms of C1, C23 over C1 plus C23, right? And for C1 here, we have 5 microfarad, and C23 we have 25 microfarad. So you can just simply adding up 5 that times by 25 and divide by 5 plus 25, and the unit would be still microfarad. Okay, the next examples, we have three capacitors connected in parallel. So to find the total capacitance, now it is easy. So if it is in parallel, we C total will be just adding up all the C's here. So we have C1, C2, and C3 in parallel. So C total would be just here. And we found out it is 6 microfarad. And A part is finished. And then determine the total charge stored in the circuit. So this become a bit more interesting, as I have that Q would be Q1 plus Q2 plus Q3, and for each of the charge, okay, for Q1 we should be able to find by C1 V1. For Q2 should be C2 V2, because C equals Q over V and Q equals CV, right? And Q3 is C3 V3, okay? But We can then see that V would be equals to V1 and equals to V2 and equals to V3 because all of them are in parallel, right? Because all the capacitors are in parallel. So they have the same, they share the same voltage then. And that voltage is 10 volt. So that Q or the total charge of the system would be just Q C1, C2, and C3. And when times by V, we have what we want. Okay. And for C, the charge stored in the individual capacitor. So we just simply having Q C1V like C1. If C1 is 1 microfarad and V is 10 volt, okay, so then we have that 1 times 10 would be 10, and the unit microfarad and volt. Farad and volt, okay, would be the unit of Coulomb because because looking from this formula, I have capacitance in the farad unit, in farad or F unit. We have V in volt unit, and we have Q in Coulomb unit, right? So farad times volt is Coulomb, but if we have this micro, okay, this mu, it just means 10 to the minus 6. So when I try to times the unit microfarad with volt, right, and the micro or the scale will be moving along with the product, right? So farad and volt, you have C or you have Coulomb, right? So and micro is passed down here, right? So that Q1 is CV and is 10 microcoulomb. Okay, and then I will let you just find the C. Let's just find the Q2 by C2V and Q3 by C3V, right? And the answer should be straightforward enough. Okay. Then in this example, find the total capacitance of this combination. Okay, so then let's start with maybe we try to combine these parallel first because it is easy, right? So combining these two, right, will give us the system with this guy 8 microfarad and this guy 1.5 microfarad, and adding up 15 and 0.75. So that would be like 15.75. Okay, then it seems that we have no choice, but just try to combine the capacitance of what connected in series. Okay, so combining like 15.75 and 1.5 together, yeah, I reckon that you can calculate it in this way. So 1575, 1.5, and divide by 1575 plus 1.5. And the same here. We should have that 5 times 3.5 divided by 5 plus 3.5 would be the combined capacitance of these two. Okay, and if I say this is X, and if we say this is Y, so the C total, okay, would be X plus 8 and plus Y, because all these three are connected in parallel, right? Okay, so then what you do is to find whatever X and Y are, right? And don't forget to give the unit of microfarad to him, right? So this is for you to find out. And after finding out X and Y, you can have the C total, and you can have some number in the microfarad unit. Okay, and then the last example is about dielectric. Okay. So here, they have that the isolated parallel plate capacitor with C0 of 5 microcoulomb is charged with the voltage Q with the voltage of 10 volt, and they kind of trying to add the material with dielectric constant of 2.2. Okay, so then firstly they ask us to calculate the capacitance. So it's pretty easy. So the new capacitance would be just the kappa factor here times by the C0. So times by the capacitance, times by the capacitance with no dielectric, right? So here it should just be the number 2.2 with no unit. Okay, and times by C0 of 5 microfarad, right? So, and that's, you have C of 11 microfarad. That's the part A. And B, how much energy is stored in the capacitor? So what we have then, we have V and C, right? So the U equation here, we should pick the one with C and V, right? And should be able to, and you should be able to find, to have 11 times 10 minus 6 joule and times by 10 volt square, right? And then we're gonna have 5.5 times 10 to minus 4 joule. Okay, as the energy that is stored within this capacitor. Okay, so that is all the equations, all the equations in this handout. Yeah. So in a nutshell, what we have been talking, okay, was simply answering the learning outcomes that I show you for all the parts, except by the RC circuit that we will talk about this on Friday. Okay. So finding the capacitance from definition, we done it. The plates, we have done it. The sphere and the cylinder, we have done the cylinder, but the sphere is using the same principle. And we have already discussed about connecting capacitance in series, parallel, and mixed circuit. And we are able to calculate the energy within the capacitors. Okay, and these are, and also the thing about dielectric, that if you change the material with different dielectric constant, it could directly change the values of C, right? Okay, so that is all for today. Okay, so thank you for paying much attention, even if my recording might be a bit horrible because now is midnight now and I'm getting quite sleepy. Okay, so thank you again, and then see you around.